a region of the universe appears to be missing. Across a map of the oldest light we can observe, one diffuse blue scar stands apart from an otherwise astonishingly uniform sky. It stretches across a patch several times larger than the fluctuations cosmologists normally expect to find. The difference is tiny in absolute temperature, only a few millionths of a degree. Yet on the largest map ever made of the infant universe, it refuses to blend in. The anomaly is real. It survived the transition from one generation of spacecraft to another. It survived new detectors, new calibration methods, and more detailed observations. What began as an unexpected feature in an early microwave sky map remained visible when a later mission examined the same region with higher precision. The mystery does not begin with a hole in space. It begins with a measurement. The map itself gives no explanation. It only records that one broad region of ancient radiation reaching Earth today is colder than the surrounding sky. Its edges are soft rather than sharp. It is not a dark circle cut into the universe. It is a statistical depression spread across roughly 5 to 10 degrees of the celestial sphere. Imagine standing beneath a perfectly painted ceiling where every brush stroke differs only by the smallest amount. Then, in one corner, an entire section appears noticeably darker. The paint has not disappeared. The ceiling has not cracked. But something about that region immediately demands another look. That is the role of the cold spot. Long before anyone searched for missing galaxies, before theories competed over what might have happened, this unusual patch simply existed as evidence waiting for interpretation. Once it had been measured, a new question became unavoidable. If this ancient light has traveled across almost the entire observable universe to reach us, could something along its journey have altered it? That question redirected the investigation away from the microwave sky and toward the visible universe lying between Earth and that ancient radiation. Astronomers began counting galaxies. Not casually, but across enormous surveys capable of mapping millions of distant systems over vast regions of space. Instead of looking for a dramatic abyss or an obvious cosmic wound, they searched for something far subtler. Density. How many galaxies occupied this particular direction compared with everywhere else? The answer was unexpected. Independent surveys revealed that the same line of sight contained significantly fewer galaxies than normal. The reduction was not complete. Stars, galaxies, and enormous filaments of matter still existed there, but over a region estimated to span roughly 1.8 billion light-years, galaxy numbers fell by roughly 20 to 30% below the cosmic average. The missing galaxies were not missing individually. They were missing statistically. On a three-dimensional map of the universe, the points simply became more widely separated. Dense clusters gave way to unusually sparse territory. There was no clean wall marking where the region began, no empty tunnel cutting through space. Only a gradual thinning across distances almost impossible to imagine. A volume that large would ordinarily contain tens of thousands of large galaxies. Instead, the cosmic landscape became noticeably quieter. The cold spot now returned with a different meaning. It no longer looked like an isolated curiosity painted onto an ancient radiation map. It appeared to sit directly behind one of the largest known underdense regions ever identified. For a moment, the investigation seemed to have found its answer. If light crossed an immense region containing less matter, perhaps that journey itself cooled the radiation before it reached us. General relativity already provided a mechanism. As light travels through an underdense region while the universe continues expanding, gravity changes slightly during the photon's passage. the light loses a small amount of energy by the time it emerges. That energy loss appears today as a tiny decrease in temperature. The effect is real. Its mathematics has been understood for decades. Everything seemed to fit. The comparison said otherwise. Researchers modeled the observed underdensity. They estimated how much cooling such a structure should produce under the standard picture of cosmic evolution. Only then did they compare that prediction with the temperature measured on the microwave sky. The two did not match. Not even close. The supervoid could explain only a small fraction of the observed temperature drop. The deficit of galaxies was genuine. The cold spot was genuine. But the gravitational effect produced by that deficit accounted for only about 10 to 20% of the cooling that had actually been observed. The most promising explanation survived, just not strongly enough. Instead of closing the case, the calculations reopened it. The contradiction no longer existed between competing opinions. It existed between two independent observations that both appeared trustworthy. One map described ancient light. The other described the large-scale distribution of galaxies. Each had passed repeated tests. Yet placing them together produced an answer that refused to balance. Researchers explored alternatives. Perhaps the underdensity possessed a more complicated internal structure than current surveys could fully measure. Perhaps several smaller voids aligned along the same direction, creating the appearance of one enormous region. More exotic possibilities reached even further. But they encountered the same obstacle: evidence. Speculative explanations could not replace measured reality simply because the standard picture proved incomplete. The strongest conclusions remained surprisingly narrow. The cold spot exists. The foreground underdensity exists. The ordinary gravitational effect expected from that underdensity appears too small to explain the full anomaly. Beyond those statements, confidence begins to fade. The exact three-dimensional distribution of unseen dark matter inside the region remains uncertain. The detailed geometry of the underdensity continues to be refined. More elaborate explanations remain mathematically interesting, but lack independent confirmation. The investigation reaches a boundary. Not a boundary imposed by imagination. A boundary imposed by measurement. The original microwave map returns one final time. Nothing about it has changed. The same diffuse blue region still occupies the same portion of the sky. The spacecraft recorded it faithfully. Later instruments confirmed it independently. The observation remains as solid as when it first emerged from the data. Its meaning, however, has changed. At first, it seemed to mark an enormous hole in the universe. Later, it appeared to point toward one of the largest known cosmic voids. Now it stands for something more precise. A place where two extraordinary maps of reality agree that something unusual exists, yet refuse to agree on exactly why. The blue scar has not become smaller. The evidence around it has become sharper. That is why the cold spot remains one of the most compelling boundaries in modern cosmology. Not because it proves a hidden universe, a tear in space, or any extraordinary claim beyond observation. It endures because even after our best measurements, the oldest light in the cosmos still carries a signal whose full story has yet to be written.